Hello, everyone. So, I don't know what happened to my background. This is normally a black background. So, anyway, this is our discussion on current measurement and a little bit about describing currents. So, we're done talking about all of the intro stuff. We're going to get into the more hardcore thing here. So, we're going to talk about what we think about when we study currents. We'll talk about ways of measuring ocean currents, and we'll talk about ways to describe currents. So, give me a sec. We'll go to the next slide, which is going to be very hard to read, and I very much apologize for this. So, anyway, our ocean currents description. If you could read this poor silly thing, it would say objective 3D picture of the movement of ocean water. And that's really our objective. This is what we want to be able to do when we talk about currents. So you have to think about the horizontal movement and the vertical movement of water. So underneath that, it would say things to think about. And so the first thing that's listed is the time interval. So how long are you going to be studying these to be able to really describe them? Do you want to do a short time interval? That's going to only be hours, days, or weeks. That's really good if you're looking at eddies or tides or something like that. But if you want to do something bigger, you want a long time interval. You want more like 1 to many years. And that's important if we're looking at like deep ocean circulation or how does deep ocean form, the movement around gyres. You want to do more of a long-term stay with that. You may also want to look at seasonality issues in there as well. And then the next thing that has on here on things to think about is what can we measure directly? We're measuring speed and direction directly. Everything else we're sort of inferring about. So there's lots of problems that we face, which is our next thing. The first thing is that things are constantly changing. Things are different from place to place and over time. Even within a matter of hours, things can change drastically because of things like tides. But even in the open ocean, things are changing because of seasonal changes in wind patterns or storms going by and such. Another issue or problem is the limited number of test instruments and personnel. Equipment is expensive. Maintenance of said equipment is expensive. And there's only so many people out there who are trained to be able to do this. And, you know, it's not the cheapest thing to do. The next problem is to get constant simultaneous image of the entire Earth, and that's very difficult. We can to some degree now, but you're only doing the very surface waters, which is not the same as looking deeper into the ocean or really understanding what the currents overall are doing. So we have two major ways of measuring currents. So our first one here, I'm going to write this so you can see it a little bit better. These are Lagrangian methods. And here what we're using are devices that are going to float with the currents, and it will move along with them. Think of it as, it could be a message in the bottle, or even better, a low-jacked message in the bottle. So you can see what it's doing over the entire time, which is what you see here. Our other method is referred to as Eulerian. And here the device remains stationary, and the water just flows past it. So it could be like a current meter, or putting a buoy out in the water. Charts are created based off of Lagrangian methods or Eulerian methods look very different, as you can see here. So one of the things you notice here with the Lagrangian is it starts at a point, and there's actually lots of them in here, and it continues to move along. So you can actually see what one particular device is doing. So there's another one here, and there's one over here, and there's probably lots of other ones around here. Eulerian methods all have a single point, and there's an arrow that comes off of that point. Okay, you see a single point, and the arrow comes off of that point. The length of the arrows are telling you how fast it's moving, and so you can see like this area, the flow is really slow. Right here along this border, and the colors are temperature. So right here where there's a big difference in temperature from the more blue-greenies to the reds, notice the flow is really fast. And this is pretty standard because remember, it's that gradient which is driving the flow of winds. Well, that gradient also drives the flow of water. So you're going to have a lot of flow through there. Another note is on Lagrangian methods, if you don't have a GPS device on them, so let's say I'm using what we refer to as a drift card. It's just a little block of wood that has some information on it to report where it lands. Those, I only know where I dropped it and where it ends up. I have no idea what it did along the way. Okay. This one's really hard to read. Okay. So this is an example of Lagrangian methods. We're going to talk about different ways. This is an interesting one. It's not done all that much, but it's a decent example. And so here we have the displacement of a ship. Okay, so this is point A. This is where it's starting off at. So ship is starting at A and it sets sail towards point B. Okay, so this is the direction that it's going in. It's trying to go in this direction. But they're going to be traveling for about an hour. And while they're out, they don't bother to check their GPS. They're just like, I'm going in this direction. I'm just going to keep going straight. Okay. The reality is they end up over here. Okay. And so the reason that they don't end up where they're supposed to be going is because of the Coriolis effect. It's the currents are pulling them, well, sorry, not Coriolis. This is the currents. So the currents are pulling them in a different direction. So we can look at this line here and we can determine the speed, which is the length, so the distance between where it should have ended up and where they actually end up. And you can determine the direction by looking at this angle. Okay. So this gives us the direction and the speed of the current in this location. Okay. Okay, so these are some other examples of Lagrangian devices. These are referred to as drift bottles. Oops, hold on a minute. Left down R. Okay. So, drift bottles could be anywhere from, that non-scientific message in a bottle idea. There are things like current drifters, which fall in this category. These are commonly used by physical oceanographers. They're originally placed at sea with a weight on them to keep it upright in the wind. So notice here, there's a weight here. Here, this comes down. There's a weight down here. And so there would be a reply card. So if you saw it, you could let the researcher know where it was. And oftentimes they were not, had no location device. So you just know they started here, they ended here. Now some of these have what are called the drogue, which is the weight. What a drogue does is it weights it to a specific depth. So let's say I'm interested in knowing what the currents are like at 200 meters. Well, I would drogue it so that at 200 meters, is where most of the weight is, and that's what's going to drive the movement of this drifter. So it's one of the issues that I've had a lot of, is that when you look at what people report for surface currents, is they were usually drove somewhere between 500 and 200 meters. Between 50 and 200 meters. But those are the surface currents. That's not telling me anything about material that is floating along the surface, because material that floats along the surface is being driven a lot by wind, which doesn't always, as you know, act the same as the current itself. So where plastic material is going is really a mixture of the movement of the water itself, the current, and the wind at the same time. So it's a little more difficult than just looking at, oh, well, surface current says that it should do this. Well, there's more to it than that. Another thing is that drifters often had a flashing light or reflector on it. And these could be used to be tracked by a dedicated ship who actually just, drove around looking at them. They often can carry additional equipment that can measure things like temperature, salinity, dissolved oxygen. Now, of course, you can have a GPS device associated with them, and that allows researchers to actually never go to sea, and they can have someone else deploy them. They can sit back in their offices and just watch everything. By the way, I have done this. We helped some people in the Dominican Republic to create drifters. They deployed them, and then I could watch them. The ones that we created here, we deployed and we watched. And by the way, it can be quite addicting. The only thing is the drifters are limited in how long they're going to provide any information, because of the fact that it's limited by its battery life. There are some drifters. Oh, and I never updated this, but that's okay. We can go with what I have here. They can actually move up and down in the water column. And so some will stay at a specific depth and send out sound impulses that can be tracked by a dedicated ship using a hydrophone. But then we have this. This is called Argo. Argo is a broad-scale array of these temperature and salinity profiling floats. It's an international project. It began in 2000. So at this point in time, this was last year, we had 3,921 floats out there. You can go onto Argo's website and you can see how many there are at any point in time. But they travel down to a depth of 2,000 meters, and they'll stay there for about 10 days. And then over a 6-hour period, they'll rise back up to the surface, taking a profile along the way. Then it'll transmit its data back to the main repository. And then once it's fully downloaded, it'll get a signal back. And that signal tells it to go all the way back down. It'll take another profile on its way back down. It'll stay there for 10 days and then come back up. So it's taking all of this data, and it's able to conduct about 150 cycles. And they're really working because you can see we have thousands of floats out there at any point in time. They're trying to work on a good retrieval system to be able to recollect them, because it's a little bit of adding garbage to the oceans that we're trying to study and understand better. So I'm happy that they're doing that. So another thing that has been done is to track spills. So, for example, oil spills. So these are accidental in nature. The Deepwater Horizon spill actually provided a lot of information on currents, including this interesting little tidbit. So here is where oil is thought to be located, this pink and this black area. And we spent a lot of time looking at these charts, which we'd been collecting for a very long time. And one of the things that we always thought is there's what's called a loop current. We'll be studying this later. It comes in. I need a different color. Hold on a moment. I can do white on here. Okay. So it comes in here, it loops around, and it comes back out. Okay, so it looks like that. And this is always how we thought the loop current behaved. But then we started seeing this. Every so often, it just does this. And this loop breaks off. And we actually never knew that until the Deepwater Horizon. It also gave scientists a chance to test out different models. These are 4 different models that predicted current movement to see which one really works the best. We learned a lot, actually. We figured out that our idea of where the oil is not always correct. A particular scientist decided to hijack a research vessel. No, it wasn't me. And went out and sampled areas, like this, that looks like they have oil in it. And what it turns out is what we were looking for were sheens on the surface, because oil usually leaves a sheen. And so they collected in these areas that it looked like the oil was. And the reality was there was no oil there. These sheens were actually the result of lipids that were being produced by algal blooms. And we had no idea that it happened before. So we learned a lot, actually, during these projects. Another thing that has been used to track spills are dye. Oops, I gotta change that color back. Are dye studies. And dye studies are done on purpose. So you can use radioactive tracers like radon, or you can use dyes. I'll show you an example when we talk about rip currents, where people have used dyes, colors. You can actually see it go out and come back in. So there's all different types of dye studies. Another way of tracking spills are cargo spills. So I'm going to give you guys a couple of examples. These are also completely accidental. So in 1990, 5 containers with 80,000 Nike sneakers were knocked off of a ship coming from Korea. So it happened about, well, I'm not really, I think it happened in here if I remember correctly. And about 6 months later, they started washing up on the beaches in Oregon and Washington, about 1,500 miles away. The shoes were not tied in pairs, and because of their nature, they actually go for about $100 a pair. They used to have swim meets, actually, to find matching pairs. So these were used to track currents. So, I was wrong. This is where the shoe spill happened. So, number 2 here, 250 were recovered on March 26th in 1991. Number 3, 200 were recovered on May 18th, 1991. On 4, 100 were recovered between January to February 1991. So those were, actually the first ones came in at 5. 5, there are 200 recovered November to December 1990. So you can sort of see how they came in here and they went up. And then the rest of them came down this way. So there were 200 recovered February to March of 1991. 150 were recovered April 4th from 1991 for number 7. Number 8, there are 200 recovered from May 9th to 10th of 1991. And then several were number 9 here. Several were recovered from January to March of 1993. And in 1994, they started showing back up over here. So this sort of gives you that idea that you have this current that comes around here and over here. Okay. Another example was 1992. And so there are 29,000 rubber ducks, turtles, and other bathtub toys that were accidentally released. So we have little number one over here. 29,000 ducks left China in 1992 and fell off of a boat in the Pacific, and 10,000 of them drifted north. 15 years later and 17,000 miles later, the bath toys are now on course for the British Isles. Here, number two, 19,000 go south and wash up in Australia, Indonesia, and South America. So you can really see the fact that, they can travel pretty good distances. Similarly, natural disaster debris is another thing. So this is a next one on the tracking spills idea. And so, for instance, material from Japan tsunami has been arriving in Alaska, Canada, California, and Hawaii. So this is looking at the red here is year 1, the orange here is year 2, the yellow is year 3, the light blue is year 4, and the violet is year 5. And this is just a picture of some of the material that's being washed around. And so there's also wrecks. So for instance, we talked about the Jeanette, and then there's one that doesn't show up here and here, and that's the garbage patch. So for instance, garbage tends to accumulate in areas of low flow. So we know the whereabouts of the North Pacific garbage patch right in here. So this is an area where material is converging together. And so islands in those areas tend to pick up a lot of this garbage. And so this is just an example here of some of the garbage in some areas. Another example for Lagrangian methods are research submarines, and really just one. So this particular one is the Ben Franklin. And so this was in 1969. That's what this picture is right here. And it traveled from Palm Beach, right here, starting July 14th, 1969, and it traveled out to here. So it took 31 days for it to travel, and it traveled 1,444 miles. And what they did is they designed this to drift along at neutral buoyancy at depths of 600 to 2,000 feet, or 180 to 610 meters. There were 6 people on board. So mind you, 6 people trapped in this thing for 31 days. And its purpose was to really understand this Gulf current. As you can see, it doesn't necessarily travel in a straight line. Okay, so let's talk about the disadvantages of Lagrangian methods. Okay, so first up, and since you can't really read this, ship/satellite time may be required. And satellite time is expensive. So I paid for my satellite time up front, which is about $500 per device. So it does cost a bit of money. Wind is a factor. For anything that drifts along the surface. You really, if you want to understand oops, sorry. If you really want to understand things, typically you're going to need a long-term study, usually years. There's the monitoring and recovery, and I will say plus maintenance of it. Drifters have to be maintained, recovered at the end of their experiment, preferably. You're going to be monitoring it, which takes time and money as well. And so if it's not monitored, so you're trying to go cheap, then you don't know what it did. Between, I put too many AEs in there, between deployment and recovery. Okay, you don't know what it did. It's a big question mark. And that can be frustrating. So let's talk a little bit about our Eulerian devices. So there are some that only do measurements at a single depth. And so these, remember, are stationary, and they just read the current that passes by them. They're not going anywhere. And so this is an example of what's called a current meter. So you've got to have something to support it. There's a rotor that's going to spin around, and then off of that are these dials. And these dials are going to spin with the rotor to record what the speed is. Now there's electronic ones that do it a little bit differently, but when we get back to the lab, remind me, I'll show you what one of these looks like. And then you have the vane here, and the vane is going to line up with the current, so that will give you your direction. In 1988, these devices cost about $8,300 each. They are cheaper now, but they're still not that cheap. So if you want to measure at multiple depths, you use what is called an ADCP, which is an acoustic Doppler current profiler. These can be attached to the bottom, or they could be attached to something and point down or up or horizontally to look at the currents across the mouth of a bay. They have a lot of capabilities. They've been commercially available since the 1980s. And what they do is they measure the water current velocities, speed, and direction over a depth range by using the Doppler effect of sound waves scattered back from particles that are moving in the water column. A sound wave has a higher frequency or pitch when it moves to you than when it moves away. You hear the Doppler effect when a car speeds past with a characteristic building of sound that fades when the car passes. The ADCP transmits pings of sound that are at a constant frequency. The sound waves bounce off of particles moving through the water column and reflect back to the instrument. Because of the Doppler effect, sound waves that bounce off of a particle moving away from the profile will have a slightly lower return frequency, whereas particles moving towards the profile will have a slightly higher return frequency. The difference between the frequency of the waves that the profiler sent out and the frequency at which they returned is called the Doppler shift. The Doppler shift is used to determine the speed at which the particles, and hence water, are moving either towards or away from the profiler. Some sound waves will travel further in the water column and bring back information on currents that are further away from the ADCP. So ADCPs can look at currents throughout the water column, and when you set up your your ADCP, they have built in what are called bends, and you can you have X number of bends. So you have 4 bends, you have 6 bends, usually something along those lines. And you can tell them what depths you want your bends to be. So let's say I want a bend to be between 4 meters and 6 meters away from my device. And I want my next bend to be 6 meters to 10 meters from my device, so on and so forth. So I tell it that. And so it figures out what frequencies it's going to use. These are my bends here. And so it can tell me that in this area right here, the water is traveling in X speed in X direction. In this area here, on average, the water is going in at X speed at X direction. So those are the bends. These are very expensive. They can be about $80,000. So they're not cheap. And so we don't have one. So there are different ways of describing currents. There are 3 things that we always give. We always report direction, what's called discharge, and what is called, well, what we think of as speed. So for direction, typically we report wind direction and current direction. So remember, for a wind, a north wind blows north to south. So a south wind blows south to north. For the current direction, remember, a northerly current flows from south to north. A southerly current flows from north to south. Discharge here, I'm going to give you a definition here. This is the rate of flow. Or you can look at it as volume per unit time. Okay, so we use units called Sverdrups. Now let me do that. Sverdrups. Sverdrups. We abbreviate it SV. So 1 Sverdrup equals 1 million cubic meters per second. The Gulf Stream, for example, has a discharge of 55 Sverdrups, which is 300 times that of the Amazon River. So for speed, we tend to show this graphically. So here you can see this white is the fastest, and it has the longest arrows. So you can really see there's a really fast current that's flying right through here, and it sort of spreads out a lot, in this area. Whereas in these areas, there's very little current. This data is from sensors I'm going to take that back. This is data that was, this is satellite data. Speeds are reported numerically, so you could have miles per hour, you could do kilometers per hour, you could do meters per second, feet per second, centimeters per second, or you can use a knot. So I want to talk a little bit about the origin of the term knot. It's an old-fashioned method used to measure a ship's speed. So what they did is they used a block of wood tied to a rope, and at regularly spaced intervals they had knots. So you threw it out, and it was the number of knots that passed through your hand in 30 seconds. That was your speed. So if 10 knots passed through my hand in 30 seconds, it was a 10 knot current. Okay. So the term knot is still used today. So 1 knot equals 1 nautical mile per hour. Okay. In the Gulf Stream, if the Gulf Stream were traveling at 9 knots, then the speed would actually be about 10 miles per hour. Because there's actually a difference between nautical miles and statute miles. There's a paper that I want you guys to read. I'll post it online a bit later. And we'll talk about when we get back on Tuesday of next week. I'll also give you an extra credit along with this. So thank you guys. Have a great day, and I will talk with you all later. Bye.